Here is a question number 18. What must be the characteristic impedance of a matching transformer to connect a line of 100 ohms characteristic impedance to the load of 120 ohms? The question can be illustrated like this. There is a transmission line whose characteristic impedance is 100 and there is a load of 120 ohms. I want to connect these two. I cannot connect them directly because there would not be any impedance matching. There would be a reflection if I connect them directly. So that is the reason why in between them I should insert some impedance matching transformer. Generally the very popular impedance matching transformer is a quarter wavelength impedance matching transformer. That means between the transmission line and the load I need to insert the section of a transmission line whose length is lambda by 4 and whose characteristic impedance is Z0 dash. And the design formula here is the characteristic impedance of this quarter wavelength transmission line must be, it is represented with the Z0 dash, must be a geometric mean. This is a formula. It is referred as a design formula. This is a design formula. The characteristic impedance of this quarter wavelength transmission line must be a square root of Z0 into ZL. And if you just substitute the values of this Z0 is 100 here, it is 120 here, just make an approximation. Here it is 10, here it is 11 approximately. So this will turn out to be 110 ohms. If you place the section of a transmission line, quarter wave length of a transmission line whose characteristic impedance is equal to 110 ohms, then you can provide some impedance matching. This is the answer. Thank you. Okay. Here is the question number 21. In a rectangular waveguide of cross section A by B, the phase constant along the axis of the waveguide is given by B subscript Z, beta subscript Z is equal to square root of omega by C whole square minus pi by A square radian per meter. Assume the medium inside the waveguide is filled with the air dielectric whose phase constant is beta is equal to 10 pi radian per meter. If the broader dimension of the waveguide is given as A is equal to 1 by 8 meters, then determine the group velocity. Okay, first, this is given here. The phase constant, this is the phase constant inside the waveguide is given, or this is the phase constant along the axis of the waveguide is given. Here, there is a two-step procedure for this problem. In the first step, you need to find out the guided velocity, or it is also named as a phase velocity. And after that, you can find out the group velocity. Here, if you compare this one, this is the phase constant along the axis of the waveguide. If you compare this one with the standard form, the standard form for this one is, it is called a beta bar, or is also represented with the beta z, which is equal to square root of omega square mu epsilon minus h square. By comparison, you can say that we know that beta is equal to omega square root mu naught epsilon naught, which is also can be written as omega by c. So if you compare this one, and it is also given the beta value in the question as 10 pi radian per meter, so which is equal to omega by c. So here you have got a omega by c value, and this value is also already given in the question. Just substitute this omega by c value as it is already given, it is 10 pi square, and a value is 1 by 8 square. If you simplify this one, this is a phase constant along the axis of the waveguide, or beta bar, which is equal to 6 pi radian per meter. Once you have got a a phase constant inside the waveguide or phase constant along the axis of the waveguide, you can find out what is called a phase velocity, or it is also called guided velocity, which is equal to omega by beta bar or omega by beta z, which is equal to, where omega can be written as beta into c divided by beta z. Beta is into z, beta value is already given, into c is 3 into 10 to the power of 8. The c value is 3 into 10 to the power of 8 meters per second. And if you simplify, just substitute all the values, you will going to get the phase velocity, or it is also called guided velocity. And once you have got this phase velocity or guided velocity, to find out the group velocity, there is one more formula where the phase velocity into group velocity is equal to intrinsic velocity square. Here the intrinsic velocity is the velocity of the light, and from here you can find out the group velocity as c square by vp, which is equal to c square 16 by 5 into 10 to the power of delta 1.8 into 10 to the power of 8 meters per second. That means the group velocity is 1.8 into 10 to the power of 8 meters per second is the answer. Thank you. Here is a question number 25. Calculate the maximum directivity of antenna. The power pattern of the antenna is given by u of theta comma phi is equal to sin theta sin phi into sin phi, where the theta is ranging from 0 to pi, comma phi is ranging from 0 to phi, and it is 0 when theta is ranging from 0 to pi, comma phi is ranging from pi to 2 pi. And the options are given. Option A is the maximum directivity is 4 and occurs along the y-axis, and option B is maximum directivity is 4 occurs along the z-axis. Option C is maximum directivity is 1.5 occurs along the y-axis. Option D is maximum directivity is 1.5 and occurs along the z-axis. So first we need to find out the maximum directivity, and from there we will find out the directivity. Okay. To find out the directivity, you must know what is the total power radiated. Here, power intensity is given. This is power intensity. That means it is defined watt per steradian. It is a watts per steradian. To get the overall power, you need to integrate over the steradian. This is a steradian. So it is a closed surface integral of u of theta comma phi into d omega, where d omega is sin theta into d theta into d phi. and just take the integrals here. It is u of t is u of theta comma phi is sin theta into sin phi, and already sin theta is there already. It will become sin square theta into sin phi d theta d phi. If you integrate by taking the theta value from 0 to pi, phi value from 0 to pi, for the integral from theta is from 0 to pi and phi is from phi to 2 pi, that integral will go 0. Only this integral will remain. If you integrate, and in the place of sin square theta, if you substitute 1 minus cos 2 theta by 2, and if you integrate nicely, you can take 1 by 2 out. The integration of 1 with respect to theta, separate out the variables, integrate with respect to theta and phi. Integrate this one with respect to theta and integrate this one with respect to phi. It will become theta minus 1 by 2 into sin 2 theta, where the limits are ranging from 0 to phi, and the sin phi integration will become minus cos phi, where the phi limits are ranging from 0 to pi. If you substitute upper limit minus lower limit, it will turn out to be pi watts. Okay, so you have got a total power which is radiated. Okay, and we'll go back to the definition of this directivity. The directivity definition is radiation intensity by average radiation intensity. The radiation intensity is u of theta comma phi. The average radiation intensity is given by power radiated by total steradian is 4 pi. So the directivity theta comma phi will turn out to be 4 pi u of theta comma phi by power radiated. You know the power radiated, you know u of theta comma phi, just substitute the values here. U of theta comma phi is given as sin theta into sin phi, and total power radiated you have calculated as pi. Okay, and if you substitute here, the directivity will turn out to be 4 sin theta sin phi. The question here is asking what is the maximum value of directivity. Obviously the maximum value of directivity will be 4. That happens when the theta and phi are pi by 2. And is asking in which direction, which axis. Suppose if you recall the spherical coordinate system, if you want to have theta, here the theta is defined with respect to z axis. Here the theta is, if the theta is 90 degrees, here it is pi by 2. This will go into direct along the y axis, and if the phi is defined with respect to x is pi by 2, the theta is equal to pi by 2 and phi is equal to pi by 2 are showing y axis. So when these two becomes 90 degrees, this theta here is 90, phi here is 90, and the directivity will become 4. The maximum value of directivity occurs when the theta and phi are 90 degrees. That means when the theta and phi are 90 degrees, that are directing towards the y-axis. So this is a conclusion. The conclusion is the maximum value of the directivity is 4 and occurs along the y-axis. Why? On the y-axis, theta value is pi by 2 and phi value is pi by 2. So here you need to remember this formula. That is the idea of this question. Thank you. Here is a question number 48. The statement number 1 is for pure reactive, it's a reactive, comma, open and short circuit loads, VSWR pattern has 0 voltage minima. The statement number 2 is for pure reactive, comma, open and short circuit loads, the magnitude of reflection coefficient is unity. Now let us do some analysis here. These are the two statements given. So here the things need to be focused. It is a pure reactive, open circuit, short circuit loads, and there is a 0 voltage minima. And for pure reactive, open circuit, short circuit load, the reflection coefficient is unity. If you consider a pure reactive load, that means it could be a pure inductive load or pure capacitive load, plus or minus JXL. If you find out its reflection coefficient, the formula is ZL minus Z0 by ZL plus Z0. Just substitute ZL value. If you take the magnitude, this will turn out to be 1. That means the magnitude of the reflection coefficient is 1 for pure reactive load. Let me check out for the open circuit. For the open circuit, load impedance is infinite. If you substitute here again, this will turn out to be 1. For the open circuit load, it is 1 again. The magnitude of the reflection coefficient is 1. And let me check for the short circuit. For the short circuit, load impedance is 0. If we substitute here, you will going to get the reflection coefficient is minus 1. That means the magnitude of the reflection coefficient is 1. That means the second statement is correct. For pure reactive, open circuit and short circuit loads, the magnitude of the reflection coefficient is unity. This statement is correct. And let me check out about its VSWR. The voltage standing wave ratio, by definition, it is magnitude of the voltage maxima by magnitude of the voltage minima, where it is turn out to be 1 plus reflection coefficient magnitude by 1 minus reflection coefficient magnitude. If you notice for all these three cases, that means for the pure reactive, open circuit and short circuit, the magnitude of the reflection coefficient is unity. If you substitute that value here, that means 1 plus 1 by 1 minus 1. It is 1 plus 1 by 1 minus 1. Numerator will become 2, denominator will become 0. If you compare this one with the definition, that means the definition is V maxima magnitude by V minima. That implies that if by comparison one can notice that the voltage minima is 0. That means when the transmission line is terminated by the pure inductor, pure capacitor or open circuit or short circuit, the voltage minima is 0. The voltage minima is becoming 0 because the reflection coefficient magnitude is becoming 1. That means here if you observe this statement, for pure reactive, open circuit and short circuit loads, VSWR is 0. This is true because the magnitude of the reflection coefficient is 1. Since this is correct and this is the actual explanation for this one, as the magnitude of the reflection coefficient is 1, here it is 1, 1 minus 1 will become 0. That implies voltage minima is 0. That means statement number 1 and statement number 2 are correct, and the statement number 2 is a correct explanation of statement number 1. Okay, option A is the answer. Thank you.